Okay, yeah, we can. I guess we'll get things started. Uh, so I'm just gonna give a few slides to sort of get things started. Actually, mostly about Q farm and some of the things we're doing there, and maybe some topics for discussion at the end. So I just wanted to. So this workshop and this kind of series of workshops is organized by Q farm, which is kind of a backronym for Quantum Fundamentals, Architectures, and Machines, and it's kind of our quantum entity on campus. And I would say we really are trying to, I think, both locally and broadly initiate a lot of communication between kind of fields. I think quantum sort of spans a lot of different things, and I think this workshop is a great example of that, both in terms of applications and in terms of disciplines. So just some of the things we do is we have a seminar series that's really attracted a ton of students and postdocs and faculty. It's got great attendance. Another fun aspect is that we've managed to have an exchange across the bay between Berkeley and Stanford. And there's no tree killings or anything that have happened yet, so that's been good. We also do a career fair, which has been very successful. And we're starting to do more things to let people know what's out there, what are the opportunities in quantum, but also beyond quantum. Another thing that we've done that's been, I think the other piece, so that's kind of community building. I think the other thing is to really try to initiate new research directions. And I think, and one program that's been, is a new program, but it's been already, I think, quite successful, is our seed grant program. So it's an internal thing, and it really tries to group people together to do kind of really not just the next thing, but just try something that might fail, and particularly across disciplines, to really get people talking to each other who might not otherwise do so. And there's teams that have neuroscientists and AI and materials and physics and all the usual things as well. So and that's been really great. We also have fellowship programs. So there's postdoc fellowship programs, Block Fellows. So everybody should have your excellent students apply to that. There's a Zhang Fellows program, which is for graduate students in quantum, and then also there's a visiting faculty program. So if if people want to, in addition to coming to give a seminar or a workshop, if you can stay longer, and there's support for that. And I think that's a great way of taking these sort of conversations that might start at one of these workshops and actually turning it into a long-term collaboration. And so, of course, everyone here is here for this workshop series. So this is one of I think our fourth workshop, and we're trying to actually keep up a pretty good pace of these, sort of one per quarter or so, and they've been really successful so far, and I'm really excited for this one. And again, we're trying to do things where it's not just sort of a workshop that you go to, where there's 10 of them a year. We're trying to pick fun topics and get interesting groups of people together to explore what's out there in different directions. So, okay, so this one. So I found, what is the millimeter wave? People define that differently. I found when I searched for millimeter wave, I got the one on the top there, and it's from 5G and stuff. So I guess 20 gigahertz and up, I guess, and I forget there was. So we're only 4G now, like in quantum at least, and maybe we can get to 5G or whatever beyond. But I stole a bunch of pictures from some of the speakers' papers and talks and things like that, and I think it represents the diversity of the workshop. So I mean, there's everything from superconducting qubits to cavities with Rydberg atoms, to parametric amplifiers, to linear accelerators for electron accelerators, to dark matter searching cavities, and all these devices to telecommunications and photonics, so and nanomechanics. So it's really just it spans every discipline, and it kind of makes sense, right? I think it's sort of amazing opportunity that we have, right, where you've got a whole region of the electromagnetic spectrum that's almost unexplored, certainly in quantum, but I think even largely in other areas, it's still been somewhat inaccessible until recently. And so I think this workshop is a good chance to share what we've been doing, but also to think about what we could do in the future. And so we tried to leave time for discussions and things like that. And just to, I think there's a lot of things to discuss. I mean, there's sort of the applications, how could we use these things for computing or for sensing and communications? And, I have quantum in parentheses because I think that's certainly an interest of mine, but I think there's probably things beyond that we can take our expertise and use it for. I think, and I'll talk about that some in my talk tomorrow, I think we're still in the phase of building good components. We don't yet really have, I think we've seen that we can do the basic things, but maybe we don't know how to do it right yet. And so I think there could be a lot of fun brainstorming about how we should proceed there. I think actually even forgetting about sort of the devices and the quantum parts, just how do we actually manipulate them? I think the microwave technology is very mature right now. You can almost just synthesize it directly, but in millimeter waves, it's much messier. Similarly, one of the challenges like we've had is just even things like packaging. Like how do you actually keep them where you want them and not have them mess everything up? And I think also another thing, I think a theme that kind of emerged organically in terms of the speakers is just coupling these millimeter waves to other degrees of freedom, to light, to sound, to atoms, to circuits. So I think some of these topics we'll hear about. I think some of them would be good topics for discussion. And with that, I'll just we can actually get started on the actual workshop and listen to Chao Lin's talks. Introduction. So, it's been one of the fun things of coming to Stanford recently is getting to meet all of my colleagues, and I've been having a lot of fun talking with Chao and about various. He has these kind of insane schemes for trying to detect dark matter and as well as other types of cosmological phenomena, and so it's always really fun to sit down with someone and sort of be like, just kind of talk about these schemes and be like, that's crazy, and like, maybe it's not crazy. And so he's going to tell us about some of these.
Right. So you had a crazy cap. So the answer is, unfortunately, not quite. So CMB detectors have been made background limited, or as we call them, blip, background limited, 2 decades ago, before I entered grad school, for both ground-based and orbital experiments, okay? So that means in order to make better and better maps of microwave background, you have to have more detectors, not better ones, okay? So the name of the game has been to deploy more and more detectors onto telescopes in better and better sites, not to make each detector better. So the background comes from, if it's a ground-based experiment, it comes from the atmosphere itself. It emits, even in the best band for microwave background, it's 10 Kelvin. So there's this 10 Kelvin background that just turned everything classical, basically. If you go to space, there's the 3 Kelvin background itself, which is also classical radiation. And the measurable is observable is basically the thermodynamical temperature of that black body. Okay, so we're basically limited by that. And for a while now, bolometers, or in particular, the superconducting transition edge sensors, micro machine thermal islands have been the dominant technology for a wide frequency range from 30 to 500 gigahertz or so, which we measure microwave background with. Just to tell people I use machine learning in my research, I generated this. So I was engaged in this war between coherent amplifiers and bolometers. You know, it happened about 20 years ago. In the end, the bolometer crowd kind of won out because the amplifiers are subject to standard quantum noise, and above about 40 gigahertz, your measurement is just decimated by standard quantum noise because you measure phase, which is not needed for microwave background measurements. You might also have heard of the term quantum technology, okay, or quantum cosmology. It is totally legitimate. So this fluctuation that you see in cosmic microwave background indeed comes from quantum fluctuation, but it is what we call Bunch-Davis quantum vacuum state, which is the ground state of inflaton field. Or if you measure gravitational wave, is the ground state of the graviton field, okay? Since the generation of this has turned classical by the process of inflation, crossing the horizon, you know, et cetera, gravitational instability. So in the end, each point here, the only measurable is the thermodynamic temperature. So it just has different temperatures at different points. There's legitimate correlations between these points that contains highly non-trivial information about the beginning of the universe. But that measurement is done classically because you only need to know the temperature of that point. Does that make sense? Okay, so it is real, but the measurement is done classically. All right, so that's the kind of filters I like to apply. Oh, that's not really quantum, that's not, you know, and so on. Well, after that, shaking heads. I have 2 left, okay? Just in the category of quantum thingy in millimeter wave, all right? So number 1. So there's a high resolution dispersive spectroscopy in space with a Cole telescope. Taking one word out, you don't need it. Yes. Right. Yeah, just anything that involves counting photons or anything that involves measuring entanglements in different places using in photons, in photonic states, okay, are probably not needed. But, you know, I'm happy to talk if you have other ideas. But this is entirely biased because I'm old, you know, I look at things, oh, that's gonna take 50 years. I won't even bother, right? Okay, so this is this kind of sharp cutoff that I apply. Well, unfortunately, the first one will take 50 years, but let me just get to that. Take one word out. You don't need kick-ass quantum detectors. And the reason is if you don't have a Cole telescope, again, radiation from the telescope will just swamp it, classical. If you don't go to space, you know, you have to look through the atmosphere. It'll just make it, dominated by thermal. And if it's not dispersive spectroscopy, the radiation itself from the source is classical enough. So you have to kind of reduce the amount of background by clicking all of these checkboxes so that your kick-ass detector with 10 to the minus 20 watt per hertz detectors are useful. Okay? Another thing to mention is we're using these instruments to measure lines in galaxies, basically. And galaxies has motion, has finite temperature, and all of that makes the line width, the sharpest line width, about 10 to the minus 4. You don't need to resolve it better than that. There's no more information finer than that. In other words, the type of spectral resolution you need for this type of experiment is around 1,000, 10,000 at best, not 1,000,000. Okay, there's nothing, because it's just a line, it's a Lorentzian line after that. Okay, so the experiment that's closest to this, needing this, was Spica, as they call it. It was canceled in 2020. Next opportunity is decades away. So you heard about JWST, putting a cold telescope in space is a big deal. At some point, JWST spends $1 million a day. Okay, so that's the type of experiment we're talking about. Okay, that also means there's lots of time to create your perfect detector system that has 10 to the minus 20th. You don't need it, or 10 to the minus 24 or something because of these reasons. But there's time to think about the possibility of using our detectors on these. Moving on. So the second one is QCD Axion dark matter searches. For this one, Dave just showed a frequency range between something like 4 gigahertz to 100. There's a compelling model for dark matter that generates an axion in exactly that frequency range. Okay, so covering from centimeter to all the way to submillimeter. So there's subtleties that I can explain a little. There's no astronomical background to make your things classical, right? And the thermal background is only limited by the cryogenic system. So you can just seal the whole thing, cool it to 10, 20, 100 milli-K. There's no background, and you're just counting photons coming out of this conversion. Usually that involves a big magnetic field aligning with the E field of your device, of your detector. For a while, it seems like, because the volume of the detector is related to the conversion rate, for a while, it seems like as you search toward higher and higher frequency, shorter and shorter wavelengths, the volume naively will scale with it. But now there's multiple methods proposed that look promising to kind of break that scaling. In other words, you can build a detector that is big, meter size, the size of the biggest magnet we can create, and yet it resonates at a frequency this much. Okay. Okay. So basically, you create a fractal-looking thing to fill the volume, as I'll explain a little. All right. Still, the count rate is low. At above about 8 gigahertz, noise from standard quantum limit again become completely dominating over. So we need your detector above 4, 5, 6, 7, 8 gigahertz. We need them to be noise-free, basically. We don't need the phase information. We just need to count the photons, or we want to know the intensity. Another very interesting thing that you might not have appreciated is, I just talked about line width earlier, from galaxies, motions, and all of that. That is a Doppler effect, okay? So that means the line width is proportional to velocity over c. For axions, the line width for this fellow is proportional to kinetic energy over c squared. So that means the axion line width around us is 10 to the minus 6. Okay, so potentially you want to resolve this, and that makes the background even smaller. So that means the requirement for detector is even more and more compared to this type of spectroscopy study of other objects. Yes. Yes. This is frequency units. Even though it looks like energy, but the photon frequency energy, same thing. So, right.
So you look for like a line with at particular.
So,
10 to the minus 6 is like the one.
yes. So this, even though I wrote it in energy units, but for photons, it's proportional to momentum, frequency, and all that. It's all the same thing for photons. So the line width is fractionally 10 to the minus 6 for axions, which is distinctly different from Doppler, which would put you at 10 to the minus 3. All right, so we need your quantum detectors above a few gigahertz, and spectrometers is the bottom line of that long-ish introduction. Okay, so the story begins regarding axions with the structure of neutrons. So this is famously what a neutron should look like, even though we show it to undergrad students. And the reason is this would have had a giant electrical dipole moment pointing that way, right? And famously, neutrons do not have any measurable electrical dipole moment. So it's more like linear. You should have started drawing neutrons linearly, not like with this angle. All right. And it is deeply related to symmetry that I have no time to explain. But the basic idea is it requires cancellation, which would have been a miracle in particle physics, unless you make an angle into a dynamical field, and QCD physics just naturally drive this angle to 0 after the symmetry breaking. And that explains why we don't measure theta anymore, or theta would have created a measurable electrical dipole moment. And that explains why we don't measure theta anymore. But at the same mechanism also induces an oscillation around 0. A field oscillating around 0 means it has a mass. So the same mechanism that explains why neutrons don't have electrical dipole moment gives axion a mass, independent of whether it's dark matter. It must have a mass. So this mechanism is the only accepted explanation at this point to the smallest of neutron EDM, electrical dipole moment. There were other candidates that survived for 20 years, but now they're being ruled out. So they look pretty bad now. So they're like long review articles about this. And in the end, it comes down to this mechanism to explain why neutrons don't look like a water molecule. All right, so that angle, theta, initial theta, the point where this field started rolling, has two possibilities in our universe. Number one, we just randomly draw a number from that theta I, okay? Number two, this theta I just randomly varies within our universe. And so effective theta I is just an average of that. So these two scenarios corresponds to what we call the stochastic window, which means you draw a number from that 2 pi angle, and our universe lives, with one angle, or the classical window in which the theta I, the initial angle, is average over 2 pi, meaning there's no more uncertainties. That explains why this first model has a range of allowed axion masses, and the second model in which you already know theta I is averaged over 2 pi gives you a line. It gives you a prediction of what the axion mass will be. And that mass is at 10 gigahertz, according to the theorists. All right, well, I exaggerated a bit, but Here you go. This is the article 2 years ago in Nature. So if you read a little bit, if axions are produced after inflation, okay, there is a unique mass that gives our observed dark matter abundance, which is now measured to better than percent level, okay? There's no more uncertainty in this other than calculation. And unfortunately, you have to do numerical calculations to figure out what the axion mass is that gives the observed dark matter abundance, assuming all of the dark matter is axion. And these fellows came up with the axion mass must be between 40 microeV to 180 microeV, or in the range of 8 to something like 40 gigahertz. That's at the beginning, the lower end of the range that Dave just mentioned. So these fellows promised an update 3 years ago to a 10% precision. I just checked the archive. Indeed, they updated, all right? And now they're saying the axion mass is between 45 and 65 microeV. If this mechanism is the correct mechanism that gives us 100% of the dark matter. Although they have this little caveat saying, oh, if there's something that I don't fully understand, the axion can be as massive as 300 microeV. So we're back to that initial range of about 8 to 60, 70 gigahertz, square in the millimeter wave range that Dave just mentioned. All right, so on the plot, okay, this is what that range looks like. Bottom is MeV, top is in frequency, and that parallelogram thing is the range predicted by these fellow. Once again, this is if dark matter is 100% axion, which is of course a big assumption, all right? But if dark matter makes up a fraction, axion makes up a fraction of the dark matter, then that line can extend to high frequency until it hits about 2 terahertz, okay? Beyond 2 terahertz, it was constrained by other things, in particular, the supernova 1987A result constrained the existence of QCD axion to below about 2 terahertz. But from 8 gigahertz to 10 terahertz, it is a compelling region to search for axions. I have a bunch of lines. So the first blue line is, if the cavity volume indeed scale as nu to the -3, then you have very sharp sensitivity cutoff. This is the ADMX experiment, which probes all the way down to the more stringent theoretical predictions. There are 2 sets of theoretical models that produce dark matter axions, and usually the lower one is considered the target. It's so-called DFSZ, and the axion, ADMX experiment has reached that level, and also experiment in Korea, CAPP. But if you want to search this range, the volume loss was a big deal. But like I said, there are a bunch of concepts, including our own, that can break that scaling. We're hoping the volume can scale as frequency to the -half, okay? And that kind of started to touch this range. And then we want your quantum detectors. We want your photon counting detectors so that we can move below this DFSZ limit. Yes. So this is the coupling. So this is the coupling strength. Okay. So you convert axion to photons, and this is the coupling strength. And these are specific theoretical models to predict the coupling strength to give you to produce axion, basically. But that coupling strength also tells you the conversion rate from axion to photons in a search. Okay, so this is what a standard dark matter axion detector look like. There's a resonator, and the E field from the resonator itself must be aligned with the magnetic field. So I have a little arrow, an E there. must be aligned with the solenoid. Otherwise, you have cancellation. So as you increase the volume, if your mode has like positive, negative here, there's no sensitivity. So the whole thing must oscillate with a single polarization, basically. Okay? And that makes it a bit hard, but you'll see how we overcome that. And you tune the resonator. And the emission from the resonator is this broad line here. And then when they line up with this axion mass, it shows up as a sharper line within that cavity resonance. Okay, and if they're off, you don't see it in this shallow hump. You tune in, and this shows up. And this has Q of 1,000,000 from that kinetic motion. This is how you do it. Typically, you use an amplifier, and you acquire the down-converted data, and you do FFT. So you have practically infinite resolution in your frequency, easily resolving your axion line at Q of 1,000,000. Okay. Above a few gigahertz, standard quantum dynamic kicks in. You really don't want the phase information that kind of mess up your experiment. So instead, you have your quantum detector here. The resolution, spectral resolution is provided by this tunable resonator now. So you just tune it, and then when they're lined up, you don't have that spectrum anymore. When they're lined up, you start to see these, events of photons, and then you tune past the resonant frequency, these things disappear. So the resonator Q provides the spectral resolution in this scenario. All right. So I want to spend 3 minutes talking about our way of breaking the volume scaling in that crazy cavity category. We have a local effort, a collaborative effort called Vera. Vera is also the first name of the woman who discovered dark matter. Okay, so we have a few ways, just to give you 2 examples. So we have typical cylindrical cavity with a tuning rod at the center. And the mode that is sensitive to axion is this TM010 mode. Of course, you all know what it is. No, I don't know. But what happens is the wave basically is a plane wave bouncing back and forth between the center rod and the outer shell. Okay, singly polarized throughout. That's the requirement. Otherwise, you don't have conversion. And then if you scale this to higher and higher frequency, of course, the volume disappears and you don't have sensitivity, right? Very sharply. So the naive idea is, why don't you just shrink the shell, the size of the shell, while keeping the diameter the same? Then you have this thing, which is still a cylinder with a rod at the center, but that rod is enormous, okay? And the shell, the distance between the 2 pieces of metal is half lambda. That is a nicely singly polarized resonance, right? And then the second step is crazier. So you kind of crumple this so that they interconnect. This thin shell start to interconnect, and then you turn it into a cone so that if you move the center part up and down, you can tune the gap sizes. I also show a cross-sectional view of the center. So see this thin shell kind of meanders around, and I'm plotting the EZ, the electric field in the Z direction, which shows that it fills the entire volume of the cavity. And then you move the centerpiece up and down, you tune that resonant frequency. So the requirement that it fills a big volume compared to lambda, and it also should be singly polarized, is what drove us to this design. The second way of doing it is to start bringing multiple of these together in contact so that they talk to each other. And these modes start to hybridize, as you guys call it, dressed, right? And you bring more and more of these together, you start to develop this global resonance, which is just a thin shell version. If you kind of think these as thin shell, right? Individual thin, and then it just oscillate as a big thing, as a whole thing, as a global mode, singly polarized, going this way. So this is direct numerical calculation. So these are the ways to break that lambda cube scaling. This is, of course, inspired by the stuff happening in Dave's group. We look at that fluke cavity, hey, that reminds me of something, and they kind of, okay. Different purposes, but it was definitely inspired after looking at those. All right, so this is a realization of that triple wedge cavity I just showed you. In order to have high Q, you must control the dimensions and the alignment of these. So in this setup, it has 19 degrees of freedom. Each one is adjustable by fine threads. So that means we're serious, right? Okay. But this is nothing compared to radio astronomy. This is standard in radio astronomy. You want coherence, this is what you get. Okay. So 19 degrees of freedom, 19 adjustment knobs, and one tuning overall. All right. We have seen resonances 2 days ago. So 2 days ago, we don't know what resonances we're seeing, but I can update in a few months, hopefully. Yes, yes. 19 for alignment, and that is nothing if you talk to a radio astronomer. All right, so this is another beehive cavity with overlapping holes, basically. And it is in our lab being measured. So this thing weighs 80 kilograms, okay? This is like, really, it's not quite feeling a meter size thing, but it is big. It is big. So if you're interested in looking at either cavity, come talk to us. We're happy to show you. And Matt, sitting in the audience, will be testing this. All right, so we break this scaling, okay? So this blue line would have been that naive volume scaling, losing sensitivity, basically, as you go to higher frequency, and at least in principle, now we can break those. All right, I should speed up a little. All right. So we did a kind of a theoretical calculation for the requirements for the detectors, in this frequency range, in this post-inflationary single line prediction, single line broadly defined between 3 and 30 gigahertz. And this is what we came up with. Okay, so we like to get the detectors or the system. Number one, we want to break the volume scaling from lambda cube to lambda to square root of lambda. We want either in the background free regime, have broadband detectors with very, very low dark count rates, almost negligible. Or if we're not quite background free, if we're still seeing thermal background, if you're seeing thermal background, you want to have narrow detector bandwidth. Yes. The efficiency in the end must matter, because if you take it to 0, you don't see anything. Yeah, but you're still coming up against finite dark count. So in the end, as long as you drop that dark count, unless you drop that dark count to completely 0, I don't know how you do that. Otherwise, so the short answer is yes. Oh, I'll have a table. I'll have the table coming up. All right. Okay. So when you're thermal background limited, still you want the bandwidth to be small, and you want to match up. You want to be only as wide as the resonant frequency of the cavity. Okay. You don't want to be wider, otherwise you're just taking in noise for no reason. So we have these two scenarios, and we also want to lower the photon background from the heloscope to below 30 millikelvin, or in that range. Unfortunately, the coldest heloscope that we achieved so far, with all the big parts, mechanical stuff, tuning, is around 200 millikelvin, not 20. Okay, so if we get all of that, I'm happy to report we can reach the coveted DFSZ target through the entire frequency range without cooling the temperature of the haloscope to 5 millikelvin, like something reasonable, reachable at 50 millikelvin. But you need both the Vera program, the volume enhancement program, and also photon counter to work. All right. So this is what a resonant haloscope looked like. Just very quickly, there has been successes already in Europe going in this direction. So this is your usual haloscope. The converted photon comes down, a coax cable getting fed into a qubit powered detector. Essentially, if you see a photon, the qubit flipped to the excited state, and just by measuring the state of the qubit, you know whether a photon has come in. And these are the counts of the photons. So far, neither the haloscope nor the detectors are very tunable or had optimized performances, but this is the initial very exciting results coming out of France in the last few months, okay, going in that direction. All right, so in the back, just very quickly, let me wrap up this other regime. So in the background free regime, if you go through the math, you realize you don't need to minimize the noise intake anymore. And you can have broadband detectors. Yes, you lose some of the conversions in the collector itself, in the dark matter collector itself. However, that was made up by having broader bandwidth. Okay, so the two effects exactly cancel. And in that regime, in the background free regime, this resonator Q drops out of the search rate equation. And in that scenario, what you do is you just put your quantum detector here and listen, okay? So this is the regime. Okay, I'll skip that. Okay, just quickly. So what happens is in metallic surfaces, I have until 10 right now. Okay, so this is what a resonator looks like. You have two metallic surfaces. What happens is if you apply magnetic field in the parallel direction to the metallic surfaces, a resonance happens, okay? And you just measure the amount of field within the resonator. So that's the resonant Axion haloscope picture. If you take away one surface, okay, and just leave one, this is what happens. At the boundary condition, you can go through the math, but what happens is there is like a Axion converted photon wave coming out of the surface, perpendicular to the surface, propagating in the normal direction. And the job of your detector is to collect and detect that photon coming out of it. So this is a preferred regime if you don't know how to make a high Q resonator at a high frequency, or because having high Q resonators doesn't matter anymore, okay? And this is how you get a large volume. There are two concepts that I want to give you as an example. So one concept is called bread. So what happens is you have a barrel and you apply external magnetic field, and wave, electromagnetic wave, just kind of emits from the surface of the barrel, okay? Normal direction, and then you have this paraboloid, inverted paraboloid, that focuses that wave coming out to a point. So this is a concept called bread, and then you put your photon detector at that location. You're gonna ask, what about the metallic surfaces here in the B field? You can do the calculation. In the end, all of that kind of get incoherent and do not sum to a point. So you can just run the entire numerical simulation as is, and you see a focus there from the converted photons. The second concept is similar. So you can imagine having a summing tree, right? Like you can build millimeter summing trees, alternating with reflectors, and the wave coming out of the reflector, if you immerse the whole thing in the external magnetic field, gets collected by the summing tree through the microstrip to a point, and then you sum up that signal. Okay, and then it goes down a microstrip or a coax cable, and you put your millimeter wave detector there. Okay, so the advantage of that over this is this fills the volume. In principle, this could fill the entire volume. And also this could have some remaining Q left, whereas there's no Q in this. Q is like 1 in this completely broadband. And here, if you get Q of 5, that's a win, a factor of 5 in survey speed. And also you can potentially fill the volume as long as you can build a summing tree, and also the loss is tolerable. Okay, so I don't imagine that to be possible at a terahertz, but it might be able to do it at 100 gigahertz. We call it the tree. Okay, inspired by the Stanford sports mascot, if you don't know what that is. All right, what is the typical count? So there are several issues. Okay, so I'll just throw this out here. So the next few slides are entirely speculative. All right, so this is what I see as potential issues for this broadband XCM searches. Okay, so there's the BRAD. BRAD is all very serious looking as a proposal coming out of Fermilab in Chicago. What is the primary modulation? So we like to have an on-off switch so that we know, okay, this excess photon counts correspond to a possible XCM signal. What is that in this picture? You can turn off the magnetic field, and if you'll see something, that means it's not from the Axion conversion, because Axion conversion only happens when you have external magnetic field. However, we're talking about 7 or 10 Tesla field, right? It is prone to systematics when you turn off a 10 Tesla field. Something might have changed, and it might confuse you. You can also look at the annual modulation. It's the orbital motion of the Earth in the galaxy, in the dark matter halo. That is also problematic. You know, you see a slightly elevated count rate when the Earth is moving one way versus the other along the galactic stream or against it. That's also subject to systematics. Famously, DAMA experiment is still seeing annual modulations, and nobody believed it is from the dark matter. It could just be seasonal variation. So both are kind of problematic, not exactly ideal. Also, the moment you throw away your amplifiers, your FFT, you lose spectral information, which is pretty sad because you can rule out parameter space, but if there's no way of confirming and convincing people this is coming from a sharp line from your data, then it's really a lost opportunity. Okay, so this is the downside of abandoning amplifiers. So how do you do spectroscopy? Q of like R of a million spectroscopy at this low rate. Okay, so this is low rate. Somebody asked about the rate. So if you have 10 meters square area in the barrel, you don't want to build anything bigger than that, I don't think. That's already pretty huge. And 10 Tesla, this DFSC model predicts 10 counts per day, not per second. All right, so that is the challenge here. So you want to be able to detect this 10 counts per day at 1 MeV. Okay, that's the typical count rate. That's why we need you in this audience. Oh, no, I didn't say that. I said, right. So that's the speculative part that comes in. Yes, you can put a filter in front of, or integrate the filter as the intake resonator at your quantum detector. An atom. Yes. Okay. You could do that. One thing that we should remember is that high Q from your photon counter does not make this Q high. That Q and this Q are different. So in order to have resonant conversion, number one, maybe you know this already, but I have a feeling that you might have heard the discussion. So this Q must be at the collector itself, okay? Yes, and the thing you can imagine doing is to insert a narrowband filter between this collector broadband and your broadband detector. I can't come up with just the ideal method. Say this is perfectly programmable, okay? And you can just make the bandwidth whatever you want and put it at the center to whatever band you want, okay? And even an ideal, say you see something and you want to know where it is, okay, where the line is, and you have a perfectly programmable filter, broadband or narrowband, then you just kind of like have a broad-ish band here or here, and then it's here, then you divide it further, the binary search, right? And then we're talking about going from Q of 1 to Q of 1,000,000. We're talking about on the order of 20 steps in this search, and each one will take as long as your initial discovery. Okay, so maybe there's other ways of doing it. Somebody's shaking their heads. That's good. If you have better ideas than this, tell me about it. Okay, but that was my idea. That's not very appealing. You could imagine doing this in an array. Just spread out your broadband signal, astronomy style, in a two-dimensional Echelle type spectrograph. Then we're talking about filling the focal plane with on the order of 1,000,000 detectors. Okay, so that's how you multiplex, right? The naive multiplexing. I told you these were bad ideas, so don't be disappointed because I warned you so. Or you kind of have a filter bank, okay? And again, you multiplex by having many photon detectors. So the best you can do with this method is R of a few hundred. Or you can have combination of the two. You have your shell, one-dimensional shell. You skip the disperser in the shell. You have a one-dimensional spectral without the order sorter, and you figure out where it is, and then you feed it into your 1D array to tell you exactly. It's kind of break the 2D problem into two consecutive 1D to get the Q of 1,000,000. But no, I don't have a good idea how to overcome this desire or achieve this desire to have high Q spectroscopy when you must have a broadband collector as your haloscope. Okay, so yeah, that's why we're having this discussion. So this is my conclusion, which is QCD-X is really a fantastic opportunity scientifically, and also for quantum, for technical inclined crowd from 3 gigahertz to 3 terahertz. This is an entirely compelling mass range to search. There's no background. Give us your best detector. We can still use them. And we should probably think about a spectrometer that can follow up to a possible discovery. I'll stop here. Thank you. Right. So I don't have the equation, but in the end, it comes down to yes. So the question is, what is the process of conversion from Exion to photon in this cavity? And the answer is you look for a term that's E dot B. So the Exion field is oscillating, and your E field is also oscillating. So if your E field is oscillating at the same frequency of the Exion, so the two oscillation cancels, so there's no phase error in the two, and then you just form an inner product of that E field onto the B field. Okay, so more often we just had a solenoid B field, which is constant. So the straightforward detector should have its E field oscillating entirely coherently throughout the entire volume. One direction up, down, singly polarized. And that is a bit hard to do, but as we discussed, it is possible. Yes. Mhm. If you have a way to achieve better angular resolution, any astronomers will take it in a heartbeat. Yes, angular resolution is an easy sell. You go to an astronomer, I can give you mini arcsecond resolution. What is the method? Tell us now. So you have to think of a way to give astronomers better angular resolution. So far it's still classical. So you might have heard about Event Horizon Telescope, in which we put millimeter wave telescopes at the South Pole, Chile, and then people are talking about Greenland now, unrelated to the political stuff, just to get the baseline, okay? But it is still a very classical, I should say, interferometric measurement, okay? There's still nothing quantum about that. So there are discussions about having photon counting detectors in the optical infrared regime, in which you might just go to so-called intensity interferometer to get resolution. And that is not completely trivial either, but it is a bit more hopeful than millimeter. So in millimeter, really the background is large, stuff are hot, okay? So things tend to be classical. But be happy to discuss if you have ideas or heard of things. Yes. A magneto. Oh. I really don't know anything about this, but you can point me offline where the reference, I can perhaps offer some, yeah, but I really have nothing to offer on this. Yeah, I have to read about it and think for a bit, yeah. Thank you. Great.
Really, it's like lambda cubed from like the nearest surface or something. Like, you have a surface of metal, and then you get lambda, lambda, vector from that. That's sort of your vector volume. Big lambda cavity, of course, but you could also either have many cavities that are coupled together and dated. But it seems like in red, they're not making anything that at all. They just have
Right.
So it feels like, especially if you're broadband, where maybe like why wouldn't you fill the whole volume up with surfaces? Either using your tricks or maybe if it's broadband, there's less.
I have to give them credit. They came up with this idea before I had those cavities. And also above 100 gigahertz or something, I imagine even this method will look pretty dicey.
Why not? But if it's like 100 gigahertz, that's like really like a millimeter cube. So they have a surface and there's a volume.
Okay, so the challenge is if you do it with metals, okay, if you do it with metals, you kind of have to collect this every half lambda, okay? Because this has different phase. So I talked about E dot B, right? So this has a different sign already, this low. So your sensitivity is really like this volume. So any broadband, yeah, you must have like this, and then your collector, another mirror collector, and kind of stack that, which is, I mean, the only way I can imagine doing it, yeah, so the only way I can imagine doing it is like this. And we haven't done it. So this is just Photoshopped, as you can tell. So we have to demonstrate, yes, we can get a broadband or low HQ. If you have 100, we'll take it, as long as it's controllable. and show that we can collect all this converted signal out of this. So this is very much R&D. So it looks very classical, but it's very R&D. But yeah, so like I said, the benefit of this is, number one, the volume will be higher because you feel it. Number two, you just take Q of 10, even if you achieve Q of 10. But the challenge is you have losses in your microstrip and you have to deal with all that summing. And in here, the geometry does it for you. But yeah, but the effective volume is this thin shell, half lambda thin shell around the barrel. Other questions? Okay, thank you. Oh, one more.
So you mentioned that you estimate 10 counts per day. That's not that accurate. So can you give us an estimate of how many counts you actually need and what would be?
How many counts you need? So if the dark count rate is 0, you just need 1. Yes, so it's really just that. Where is that slide?
You estimate
Yeah.
the property, ideally you get 10 useful counts per day.
Yeah. Right. It's 10 per day for a $20 million. What ended up being a $20 million experiment. Well, if you can give us a detector that has less than 10 dark count per day, then it's a hugely, high signal to noise detection. Yeah. Okay, thank you.